Hey everybody, let's go over this second order circuit. And I can already see it's a long problem because it's 2 questions and each one seems like a lot. Okay, so this switch is open for a long time, which means, let's just look at this right here. So for a long time, for that capacitor, the current is C dV dt. The voltage across here would be constant since the switch has been like that for a long time. So if V is constant, dV dt is 0. So that means the current going through this capacitor is 0, which means this resistor takes all of the current coming from here, right? None of it goes here. All of it goes through this resistor. So then what's the voltage across the resistor? It looks like a voltage divider, right? It looks like, right? Because we want the voltage across just the 625 ohm resistor, because the voltage from here to here is the same as the voltage from here to here. So what is the voltage across the 625? Let's see, 156.25, right? This is just a voltage divider. So the voltage from here to here would be 25 times 625 over 156.25 plus 625, right? It's a voltage divider. All right, let me pause and punch in the calculator. Okay, so that's 20 volts. So now we know when the switch is open, the voltage across, well, this resistor is 20 volts, and these are in parallel with each other, right? So the voltage across the capacitor before we hit the switch is 20 volts, and then the voltage across the capacitor cannot change instantaneously. So after we hit the switch, it's still going to be 20 volts. Okay, so now when we close the switch, what happens? Then we have, right, so this is connected here. So now we have kind of a current divider. Why don't I do a source transformation here? So I'll turn that into a current source, and then it'll just be the 156.25 ohm in parallel with the 625. Okay, so what is this? That would be V over R, 25 over 156.25. So let me punch that in the calculator. Okay, so that's 160 milliamps. Why don't we combine these in parallel? This plus 1 over 625, and then take the reciprocal. So let me punch that in the calculator too, so we have a number. Okay, so that turns out to be 125. These, the 156.25 and the 625 in parallel is 125. Okay, then let's draw the rest of it. Capacitor and then the inductor. Okay, so those 4 things in parallel. Okay, so this is a step response because there's this thing over here. Okay, okay, so if we just write KCL, try and do it quickly. So we got, let's say, going down from the top node. So minus 160. And then for the resistor, the current would be V over R. For the capacitor, C dV dt. For the inductor, we know the voltage is L di dt, but I want current. So I move dt on this side, and then divide by L, and then integrate both sides. So I minus I naught equals this, so the current is all of this. 1 over L integral v dt plus the initial. Okay, and then I don't like having this thing here, so let's just take a time derivative of the whole thing. So the constants go away, and then we have 1 over r dv dt plus c d squared v dt squared plus, this will just become v. Oh, I forgot the 1 over L. Okay, and then let's just divide everything by c to get rid of this coefficient. There you go. Okay, let me swap these two. Okay, so it's a second order ODE. Let me factor a 2 out of here so that I can write a quadratic. And let's just do some substitution. Let's call this alpha. Let's call this omega naught squared, knee per frequency, undamped natural frequency. Right, and then if the general form of the solution looks like V is A e to the some kind of st, substitute that here and here and here, then it just turns out to be like this. That's our characteristic equation, which is a quadratic. The roots are okay, but then it depends on what's happening with these two numbers. So we actually need numbers. So let me plug that into the calculator. Omega squared is 1 over LC, so omega is square root. Okay, so let me just use these numbers. So R is 125, C is 5 microfarads, L is 0.3125. Okay, so let me punch that in the calculator, and then I'll write down the numbers. Okay, so they both ended up being 800. So this is actually critically damped, right? So this is critically damped. So you can just look up. Okay, you can just look up the solutions from our lectures for critically damped. Okay, so the solution looks like some arbitrary coefficient e to the minus alpha t plus some other arbitrary coefficient t e to the minus alpha t. In this case, alpha is 800, right? Okay, so we need these two arbitrary coefficients, so we need initial conditions. V at t equal to 0 would be a1 e to the 0 plus a2 times 0 e to the 0. But what is this? We know it was 20 volts. Okay, so that's 20 volts. So actually A1 is 20 volts. Okay, so we got this. Now we need this one. So we need another initial condition, which we can use dV dt. Okay, so just take the time derivative of this. So time derivative of that would be minus 800, alpha is 800, right? A1 e to the minus 800t. Now take the time derivative of that. That's the product, so product rule. Let's see, A2 e to the minus 800t plus t times negative 800. Okay, so that, oops. Minus 800 a 2t e to the minus 800t. Okay. Do we know dv dt? Multiple choice. Right, so where do we see dv dt? Here, which means we need to look at the capacitor. Okay, so for the capacitor, we need to know the current. Okay, so this is for the capacitor. So we need to know the current in the capacitor at t equal to 0. So let's maybe take a look at, I'll just draw another picture, right? So okay, so no, 160, right? All right, so we know the voltage across here was 20 volts, which means we know the current going through the resistor for sure, right? Because the current for the resistor would just be V over R. So 20 over, what was the resistor again? 125, right? 20 over 125. Okay, so we got that. And then for the inductor, before, when the switch was open, the current going through the inductor before we hit the switch was 0, right? Because it wasn't even connected to anything. And then after we close the switch, the current through the inductor cannot change instantaneously. So if it was 0 before we hit the switch, it's going to be 0 immediately after we hit the switch. Okay, so we know the current over here for the inductor is 0. So then what is this? It's the leftovers, right? So just KCL. We got minus, let's say from the top node going down is positive. So negative 160 plus 20 over 125 plus I for the capacitor plus current for the inductor is 0. And this is 0. Okay, and then 20 over 125 is actually 0.16. So this plus this equals 0. So therefore, the current through the capacitor at t equal to 0 equals 0. Not always. That's not always true. For this particular example, it happened to be true. Okay, so how does that help us? This is this. The current through the capacitor is C dV dt. And then we want this all at t equal to 0. So at 0, at 0. So then dV dt at t equal to 0 is the current at t equal to 0 divided by the capacitance. Okay, which this happened to be 0. So this is 0. So it takes us back to this. Okay, I'm just gonna copy it. Good thing for digital tablets. Oops. Okay, so at t equal to 0, okay, then e to the 0 is 1, e to the 0 is 1, and then this is 0, so this whole thing becomes 0, and then dV dt at t equal to 0 ended up being 0. Just happened to be. So there we go. Okay, so A1 was 20. A1 is 20, so therefore A2 is 20, so 16, one more zero, 16,000. Okay, so there we go. So we got our answer. Oop, wrong one. Here. So let me just write down the answer. Let me pause and paste. Okay, A1 is 20. Alpha is 800. A2 is 16,000. And there we go. Okay, so this is the answer. That's the voltage for part A. Okay, part B, what is the current through the inductor? So that is an entire separate question. Okay, so let's just take a look at this. Okay, so after the switch is closed, KCL, what do we got? Let's replace this. Let's use the other picture. Hold on. Okay, so KCL. So we got the current from this thing. Let's say going down is positive. So minus 160 plus the current for the resistor plus the current for the capacitor plus the current for the inductor. Okay, what do we know so far? We already know the answer for V, right? From this is V. We got the answer right here. Right here. Which means we know the current for the resistor for sure. Right? It's just V over R. So this over R. Got it. How about for the capacitor? For capacitor, it would be C dV dt. So we need to take the time derivative of this, which actually we did already. Right here. We did that already. So all of that divided by C, times C, goes right here. And then plus, for the inductor, we are trying to solve for that, right? That's actually the question. Oh, I forgot to write equals 0. Okay. All right, that's what we're trying to solve for. So just take all of this, move it to the other side of the equation. Let me just go write it like this. Okay, and then I'll just flip these signs over. And there we go. Okay, so this is it. Well, I mean, we got some arithmetic to do, but that's basically how you would do it. Okay, so let me just take a few minutes. IL of t equals 160 milliamps minus 1 over R times V, which is so good thing for digital tablets, and just copy and paste there, minus C times dV dt, which is this. We already did this. There. Okay, and already there's something we need to do. Look at these arbitrary coefficients. So that's some more work we need to do. Okay, so note this though. Let me gather like terms. Okay, so take a look at anything that has e to the minus 800t. Okay, these 3 terms. So let me gather those terms. So we got minus 20 over R plus 800C times A1 minus C A2 e to the minus 800t. Okay, so notice that this whole thing is just some arbitrary coefficient. Why don't I just give it a different letter? B1. Arbitrary coefficient that we have to solve for that. Okay, now for the other terms, t e to the minus 800t. There's two of these. Okay, so we got, let's see, minus 16,000 over r, and then plus 800 c a times a2 t e to the minus 800 t. And again, this whole thing is just some arbitrary coefficient, this whole thing, which I'll just call it coefficient b2. So let me rewrite it just so it looks cleaner. So it's arbitrary coefficient e to the minus 800t plus arbitrary coefficient t e to the minus 800t. So now we have some work to do, right? What is this? What is this? And then how do you do that? We need initial conditions. So what is IL at t equal to 0? 160 milliamps plus B1 e to the 0 plus B2 times 0 e to the 0. Okay. And then we already said the current through the inductor at t equal to 0 was 0. Okay, so look, we have, actually, so we know the answer already, right? Okay, so B1 is negative 160 milliamps. So now we need the other coefficient, so we need another initial condition, which we can take the time derivative of this. So di dt at t equal to 0. Let's do this first. Okay, I paused and wrote a little bit. Well, paused just to save some time, right? So I just took the time derivative of this equation, and then I got this, and then we need di dt at t equal to 0. But what is di dt? Again, right, multiple choice. Right? dv dt shows up for the capacitor, di dt shows up for the inductor. So we're looking to the inductor, and we're looking, okay, ignore this, right? We need the voltage for the inductor, which was, where is it? Oh, higher. Oh, long problem, right? So the voltage across here was 20, and these are in parallel, so 20. Okay, so di dt at t equal to 0 is, like, let's move the L on this side, 20 over L. Okay, so let's write that right now. So this at t equal to 0, 160 milliamps minus 800 B1 e to the 0 plus B2 e to the 0 plus, that's 0, equals V for the inductor over L, and that was 20. And then we know the inductor, right? So now we have, just take B1 equals negative 160, plug it in there, solve for B2. Now we got both. Okay, so it's kind of a long problem, so pause where you need to, and then let me know if you have questions, and I'll see you in the next video.